Right, let's get started. This is the class where we get into the weeds of crypto. We started seeing number theory, which was in the last lecture, which was kind of setting the stage, and we'll really use it today. So what are we going to see? We're going to be ambitious. We're going to see a bunch of things today. We'll start with a new tool called random set reducibility. This is something that I was supposed to have told you in the last class, and my TAs were pretty upset at me for not doing so. So we'll start off with that. So the order is a little bit reversed. We'll then sort of go on to see the first new sort of cryptographic application, namely coin flipping on the phone. I'll tell you what that means. And to solve that problem, we'll need to introduce a new notion called hardcode predicates. And to achieve sort of this notion of hardcode predicates, we'll need to use random subreducibility, so the whole thing kind of ties back. That's the plan for today. Never mind what these things are. These are the theorems that we will show in this class and the next class. And, you don't even know. I haven't even told you the definition of what these things mean. So hold on just for a second. Okay, so I'm going to try sort of experimenting with this lecture, with this sort of slides and blackboard. The point being that the high-level picture will be on the slides, but I'll do the calculations on the board. Hopefully that gets involved, and we'll see how that goes. Okay, so random subreducibility. So what does that mean? So let's say you have we saw the discrete log function in the last class. So this is a function that takes a prime p, a generator g of zp star, the multiplicative group of numbers mod p, which are relatively prime to p. So this is zp star. The numbers 1, 2, 3 up to p minus 1. Each of these numbers is relatively prime to p because p is prime. Right? So that's zp star. And we saw in the last class that zp star is a cyclic group. In other words, there is a number g such that if you take g squared, g cubed, so on and so forth, it will cover all of zp star. So that's a generator, g, right? So you have a p, you have a g, right? And you have the discrete log problem is I give you g to the power x, and you have to compute x. You have to invert this, you have to compute x. That's the discrete log problem. And random subreducibility is the following question. So suppose you have a box that, where did this box come from? I don't know. Suppose you have this box that computes the discrete logarithm, it inverts this function that goes from x to g to the x for a 1 over polynomial fraction of numbers. Okay. So that's helpful, right? The 1 over polynomial is a decent fraction, so 1 over n to the 100. But n is actually the bit length of p, right? So you have a box that computes discrete logarithms for 1 over n to the 100 fraction of numbers. That's helpful, but not super helpful, right? It doesn't compute discrete logs everywhere. It computes discrete logs on a very small fraction of the group. Now, you want to... Okay, so what does that mean? Suppose this box actually did exist. That means that the discrete log function is not a one-way function. Right? Because for the discrete log function to be a one-way function, no adversary should be able to invert this function on more than a negligible fraction of inputs. Right? Here is an adversary that computes discrete logs for 1 over poly fraction. Okay, so what you want, random subreducibility is one question, you want to trick this box into computing discrete logs for you for all of zp star. Right? So, you want to use this box. The box said, well, the box is what? The box is an algorithm. The box is an adversary. It said, look, I'm going to compute discrete logs for you for this, and this numbers. A set of density 1 over p. Right? So if you just give the box a number that you have as input, you want to compute discrete log of, it could very well say no. But you want to trick this box into actually computing discrete logs for you for every input that you care. Okay? So, can you do it? That's the question. And the answer is yes. And that the way to answer this question is through a property called random self-reducibility. Okay, so that's what our first sort of topic is. How would you do it? Any thoughts? Any ideas? So I want to compute. I have a number y, which is g to the x for some unknown x, and I want to compute x. That's my goal. But there's no guarantee that this box will give me the answer x for this y, this particular y that I could. It does give me the answer for 1 over p of n fraction of all possible y's, but for this y, what do I do? Yeah, that's problematic. I can't just feed y to this guy and expect an answer. It would say, no, I'm not going to tell you. You want to check it. So that's the answer is in the title, right? Random. I suppose I have to use some probabilities. I have to sample numbers, do something, right? Random. Self-reducibility. What does that mean? Well, we'll see. I guess. Right? It'll be obvious once you see what the procedure is. So, any ideas? Typewriter. Let's go there, and you will have make sense. Yes.
You can try like randomly multiplying the number you have by numbers that you know the discrete log of, and maybe hope you end up with the number you know the discrete log of.
Sounds reasonable.
Yeah, I was thinking something similar. I think you would maybe multiply the given number by some g to the a, where a is randomly chosen, and hope that the box will give you the discrete log of this product, and then you invert the answer by multiplying g to the minus a.
Multiplying by g to the minus a. It's almost there, right? So the combination of these numbers are almost there, right? So here it is. So this is really the answer. Again, you have an imperfect discrete log algorithm, and you want to sort of make calls to it and get a perfect discrete log algorithm which gets a simple y. It's supposed to produce x such that g to the x equals 1. That's the goal. That's what I want to do. That's what the green box is supposed to do. What does it do? Like you said, like both of you said, pick a random number r, compute g to the r, and multiply y bar. So compute y times g to the r mod p. Right? So what is the discrete log of y times g to the r mod p to the base g? It is a discrete log of y plus r. Right? So let's say y is g to the power of x. So y is g to the x mod p. So the discrete log pg of y equals x. Then the discrete log g of y times g to the r is simply x plus r. Yes, that's what it is. Okay. Everyone with me? Good. All right. So if the imperfect discrete log algorithm did give you a discrete log of y times g to the r, you can compute the discrete log of y. Just subtract r from it. You know r. You just picked r for yourself. Yeah? That would be. But the question is, it is an imperfect discrete log algorithm. Who says that he'll give you the discrete log of y times g to the r? Yes, that's the problem. You think about it and you realize that y times g to the, if I pick r randomly from the interval 1 up to p minus 1, right, really these are all possible exponents of g to the number that covers all the group elements. You pick a number r at random, so pick a number r at random in the interval 1 p minus 1, y g to the r, every y is random in ZP star. Yes? If you pick r at random from 1 p minus 1 and compute g to the r, it's a random group element. And the groups have this nice property that if you take any fixed element in a group and multiply it by a random element in the group, you get a random element. The groups are nice that way. So y times g to the n, what I'm feeding to the adversary is a random element from the group. Right? Which means, right, so he promised me that he will invert, he'll compute discrete log for a 1 over p of n fraction of numbers. So the probability that the imperfect discrete log answers correctly, namely with the correct discrete logarithm, is at least 1 over p of n. Yes? Accept? So, I mean, how many times do I have to do this process? So I can keep picking 1 or 2 or 3 or 4, right? So eventually, he's going to be tricked into giving me the discrete logarithm of whatever I feed him. Then I subtract out on them. How many times do I have to do this in expectation? P of n times, really, right? So it's a coin that comes up heads 1% of the time. I toss it 100 times, I get heads in expectation. Yeah. But you know, we're not happy with expectation. We want a high probability guarantee. Right? So repeat this process, namely pick an R, compute, feed, so forth. Something like n times p of n times, right? The probability that the imperfect discrete log algorithm answers incorrectly every time is what? Is at most 1 minus 1 over p of n, which is the probability that he answers incorrectly once, and each iteration of this process is independently random, because I pick it completely random, excuse me, from 1 to p minus 1. Yes? So the probability that doesn't answer any of these times is this number, which 1 minus 1 over p of n to the p of n is 1 over e. Okay, back to line. That's most 1 over. Okay, so this is e to the minus. Okay, it's extremely small. So if I repeat this process n times p of n times, which by the way is polynomial, right? P of n is polynomial, n times p of n is also polynomial. Polynomial number of times, large enough polynomial number of times, I'll almost surely get the discrete log. For everyone. Right? For everyone. No matter which y I start with, I'll succeed. Yes? So this is how I trick the box. Yes?
What's wrong with just leaving the algorithm as just trying it once and knowing that like he's probability 1 over p given being right?
Good. So sometimes we will be in a position where we have to feed this box with multiple inputs, right? Which are all correlated. So maybe y plus 1, y plus 2, y plus 3, and so on and so forth, right? And somehow we want answers correctly for all of these numbers because we are going to combine them together, as we will see in like half a minute. So, you know, the thing with this box is that it could refuse to give you the answer for all even numbers. Okay. So if it gave you the answer for y, it will certainly not give you the answer for y plus 1. Right? So if you just use this box as is, you will never succeed. Because if you got the answer for y, you won't get the answer for y plus 1. If you didn't get the answer, you see what I mean? If you got the answer for y plus 1, you won't get the answer for y. So that could be, because the box picks where it succeeds. You want to trick the guy. Good. So a consequence of this theorem, another consequence of this theorem, this random self-reducibility, is that if the discrete log function is a weak one-way function, then it is a strong one-way function. How so? Right? So remember we saw in the long time ago, the second lecture, that any one-way function, weak one-way function, can be transformed into another function which is a strong one. So what is the difference between weak and strong? A weak one-way function is you only have the guarantee that the adversary doesn't invert everywhere. So the probability that an adversary inverts is at most 1 minus 1 over poly. That's all you have. It's a very weak guarantee. And a strong one-way function has a guarantee that the adversary doesn't invert except with negligible probability. The probability that the adversary inverts is at most 1 over poly for any polynomial. Right? And we showed that these guys are the same in the sense that you can take any weak one-way function and convert it into a strong one-way function. Right? How did you do it? You want to remember? Concatenate, right? So you take an input, a very long input, and break it up into pieces, and apply the weak one-way function on each of these pieces. That works. It works, except it's expensive. Right? If you take a one-way function on like 100 bits of input, a weak one-way function, 100 bits of input, to get a strong one-way function, you might have to repeat it. Well, it's not clear how many times a priori. It depends on the success probability of the adversary. Very long. So you will get a strong one-way function. It's very long. That's no good. So what discrete log does is, it's the beauty of discrete log is that it shows that if the discrete log function is you assume something very weak about the discrete log function. Say that it's a weak one-way function. The same one-way function, no change necessary, is also a strong one-way function. Okay? So how do you show this? You show the contrapositive. And the contrapositive is basically random self-reducibility. Let you think about it. Consequence of random self-reducibility. Again, this comes up really all over. This is an immediate consequence. Random self-reducibility is it's a really nice notion. It says you have a program that computes something for you, right? It makes mistakes on, a lot, really, 50% of the input, 49% of the inputs. Right? If it's a bit, or it's a number, 99% of the inputs it makes a mistake. And you want to trick this guy into get your own self-correct. That's what it is. Very powerful notion. Not just it was invented in cryptography, but it percolated into all of theoretical computer science. Okay, so notion one. Why is this important? Yeah, it's important because I just showed you this theorem is a concrete consequence of random. Okay, you'll see it. You'll see it, as we go along in the course, and in particular as we go along in this lecture, in this very lecture. So now you know what I mean. Yeah. Very good. All right. Good. Yes.
For random self-reducibility, is there a particular constraint on the algorithm itself?
On which algorithm? On the algorithm that tells you I'm gonna no. So that's the thing, right? I mean, it assumes nothing about the algorithm that predicts discrete log 1% at a time, or 1 over PFN at a time. It just assumes that this algorithm actually does well on some 1 over PFN. I don't even know where it does well. Right? The only guarantee is that it does well on some 1 over PFN fraction. That's the, yeah. That's the. On the other hand, if I gave you an arbitrary one-way function, right? It doesn't have the nice structure of discrete log, and you won't be able to do this random self-reduction. So it's uses the algebra of discrete log very, very crucial. Okay, good. Right, so topic number 2 is a new application. Which was, so in the beginning of cryptography, people sort of started thinking about, what are the cool things I can do with, I can sort of imagine up, right? They sound impossible, right? And yet with crypto you can do it. Okay, this is probably one of the earliest such examples. So what's the problem? Alice and Bob, right? They're not in the same place, and yet they want to agree on a random bit, okay. On a fair bit. Yeah? Fair why? Because maybe this bit represents, who's going to go shopping tomorrow. So I ask you that. But of course they don't trust each other, being Alice and Bob. Right? So how do you do it? Now, if they are in the same room, you could say, here's the coin. Even then, who picks the coin? Okay, so this is not completely clear. If I pick the coin, I could bias it in a way that it comes out to the right bit in my favor. So it's not clear at all how to do this, and certainly if the two people are not in the same place, if they are doing this remotely over the phone, it's not clear at all. Okay, so here's an idea. Okay. So Alice says, tring tring, okay, flips the pair coin, okay. B, sends it to Bob, says, Bob, my coin is heads or tails, 0 or 1, B. And then Bob says, that's very nice, here is, let me flip a coin, C, also a fair coin, sends it back to us. Then the bits that they share is B exclusive or C. You know exclusive or, yes? I mean, 0 exclusive, you know. That's the protocol. Good protocol, bad protocol? What do you think? How many, yeah.
I mean, Bob can
No,
just
yeah.
like pick where he wants the coin to come up, right? Like Alice doesn't know he's flipping a coin, right? So,
Alice doesn't know, Alice doesn't see anything. Yeah. So Bob could do whatever he wants. Right. If he wants a 1, he would send back the opposite, B XOR 1, B complement. If he wants a 0, he'll send back B XOR. That's it. I mean, it's perfect, it's perfect control for Bob. Now Alice says, look, no good. I found this trickery that you're trying to play. Let's do it in reverse. Okay? Why don't you flip a coin, send it to me. I'll flip a coin and send it back to you. Okay? And then XOR. What about it?
You get the same problem.
Same problem, except Bob is in a bad place now, right? So this doesn't work. Doesn't work. In fact, you can show that if you don't make any computational assumptions, if Alice and Bob are sort of computationally unbounded processes, there are no protocols that solve this problem. And they can always cheat. For any protocol you come up with, either Alice can cheat Bob or Bob can cheat Alice in the sense of biasing the code. This is a theorem. I'm going to prove it to you. This is a simple example. This is a one-round example, right? One could do very complicated things. Why XOR? You can do other things. You could compute n bits, and you could take the majority of these 2 bits. Why not? But any of these protocols can be biased significantly by either Alice or Bob. All right, so now what do you do? Well, crypto comes to the rescue. Right? So we start by assuming that Alice and Bob they obey the axioms of the world, namely they are polynomial time machines. Right? They act honestly, for sure, but even if they act dishonestly, they cannot do more than polynomial time computation. In particular, under the discrete log assumption, they cannot solve discrete log problems. Right? So here is the protocol. Okay. So Alice says, well, I like discrete log. I'm going to pick a random x, compute g to the x mod p, and send it to Bob. And she says, my bit, I mean, I have to have a bit, yes, we are trying to agree on a bit, is some bit of x. I mean, what is some bit of x? I don't know. We'll see in a second. Okay? So it's some function that maps x to 1 bit. That's what okay, so she sends g to the x to Bob, and then the rest proceeds in a similar way. Bob flips a fair coin, sends it to Alice. Right, so now, note that Bob doesn't know necessarily what B is, because he knows g to the x. And what is some bit of the discrete log? It's not clear. Right? So he flips a fair coin, sends it to back to Alice, and they and now what does Alice do? Alice reveals this x that she picked. And Bob checks that she isn't cheating. This x that she revealed, g to the power of this x, is equal to the number that she sent in the first message. Okay, so checks that is correct. And if everything works out, then Alice and Bob say, well, here's a coin, B XOR C. Okay, that's the. So really, what really is going on here? Right? What is this first message? What is this g to the x doing? It is a way to commit to a bit. It's a way to commit to a bit. What does it mean, commit? It's as if Alice is picking a bit B somehow. It is putting the B inside a box, inside a sort of sealed envelope, and sending it to Bob. Okay? So this has 2 properties. One, when Bob looks at this envelope, he doesn't see what the bit is, hiding. Yes. Two, later, if Alice wants to cheat and reveal something else, she can't. I mean, she's committed. I mean, there's stuff inside the box and there's stuff inside the box. I cannot change it. Right? So it's called binding. So cryptography gives you a way to achieve both these properties at the same time. Okay? That's what we want. Okay? So that's the... Okay, so does this make sense? Does it make sense that something like this would actually solve this sort of impossible sort of who goes first kind of conundrum? Yes. What?
They have to agree on the sum bit function.
Ah, very good. Yes, that's okay. Good. So I you shouldn't let me get away with with these kind of things, right? What is sum bit of x? It is a function that takes an x, a number from 1 to p minus 1. That's the range of the exponents, and maps it to a number 0 or 1. That's what it is. Yes?
Even odd.
Beautiful. Beautiful. What is such a function? Well, you can think of many such functions. Yes. Even or odd is a good one. So that's the least significant bit of x. This is the same as even or odd. It's well defined because the discrete logs, they're mod p minus 1, which is an even number. So you can check that this actually is well defined. Even or odd. All right. Now the protocol is well specified. Yes? You agree? There's no uncertainty here. Least significant bit is a function. You know it, I know it, everyone knows it. Question is does this result in a fair coin toss? That's the question. Let me see a show of hands. How many people think that this is actually fair to Alison? Okay, fair enough. How many people think it's not? Margaret, you are halfway,
It's fair.
It is fair. Okay, good. Not fair. It's sort of evenly split, yeah? Okay, all right, we'll see. Okay, so now let's see a little bit of number theory to determine one way or the other.
So Alice sends B or the result of G of X?
Which one, the first message or?
The first message.
The first message, she doesn't send B. B I keep to myself. I just send G to the X. Point being that on the one hand I'm committed to B, and on the other hand Bob doesn't see what B is. Unless he computes a discrete logarithm, which of course we can't. Assuming the discrete log assumption.
From what set is Alice choosing x?
Randomly from 1 to p minus 1. Right? It's a space of exponents. Right? Zp star is covered by g to the 1, g to the 2, up to g to the p minus 1. So, all right. Okay. Good. So, okay. So, consequence of that is that b is actually an unbiased bit a priori. Right? So, if I take a random number from 1 to p minus 1, take the even or odd, it's half probability even. At least that's it. All right. So, in an attempt to kind of see what is going on here, let's see a little bit more number theory. Yes.
How does Bob know that Alice is like choosing a random x and not just like?
So Bob doesn't have to know. So malicious Alice could pick a non-random x, and what is she trying to do? She's trying to make the bit biased. Right?
Mm-hmm.
But that wouldn't happen because the bit is the XOR of whatever she picked to begin with, and C, which is a random. So as long as Bob acts honestly, doesn't matter what Alice. Right? So Bob's C would completely randomize. So one thing that Alice could do is pick a random x with least significant bit 0. So B is always 0. It doesn't matter because the bit they agree on is B XOR C, which is random by C. Right, so this is the kind of effect we want. One thing that Alice could have done is she picked G to the X, right? Gets a C, and then she says, well, G to the X had some bit in my head. B XOR, the bit that we are going to agree on is B XOR C. I don't like it. So let me reveal a different X, right? such that g to this new x is equal to g to the what I committed to, right? So, and this new x prime has a different bit, essentially. But that cannot be, because there is a unique x. Once I committed, once I told you g to the x, there is a unique x between 1 and p minus 1 such that, okay? So I'm committed, I'm done, I'm committed. So she cannot. Okay, so this object that I hand-wavily kind of defined is called a commitment scheme, and we will see much more of it in the upcoming lectures. At this point, let me leave it at this level of precision. Okay, the number theory. So what are we trying to do? We're trying to see if this protocol that I described with least significant bits, function is secure. All right, so number theory. Okay, so we all know ZP star, it's our friend at this point. The order of the group. What is the order of ZP star? It's p minus 1. It's really numbers from 1 to 3 up to p minus 1. It's a cyclic group. Again, as we saw, there is a generator that, G. There are many generators, in fact, such that if you take G, G squared, G cubed, so on and so forth, you get the entire star. So let's peer at this a bit more closely. Okay, so again. Okay, so let's say P is 7, prime, very good. G is 3, right? So why is G a generator? I don't know, we can work it out, right? Yeah. So now I wrote down this ZP star, Z7 star, numbers from 1 to 6 inclusive, in this strange way, in this circle, right? What is this strange? I should have written 1, 2, 3, 4 up to 6, yes. What is this strange way? What is it doing? Any guesses? Sorry?
That's the order in which
The generator
the
generates
generator
this stuff. Right? Yeah. So really, this is 3 to the 0, 3 to the 1, 3 squared. That's what it is. So it's a natural kind of. Right, very good. So this is all set up. All right. So need more things here. Quadratic residues and all. So what is the quadratic? So okay. So here's the question. Here's an equation. X squared is 2 mod 7. Okay. Does it have a solution? In general, I can write polynomial equations. Here I'm asking if there is a solution. Yes.
Yeah, 3 and 4.
3 and 4. Yeah. So 3 squared. 3 is 3 to the 1. Right. 3 squared is 3 to the 2, which is 2. And if 3 is a solution to this equation, minus 3 is also a solution. Minus 3 is 4. That's right. Yeah. So either, and what about x squared equals 6? Again, you can see there is no solution to x squared equals 6. So in general, every number, that you put on the right in the place of 2 or 6, either has a solution. If it has a solution, it has 2 solutions, or it doesn't have a solution. So that's fine. And this fact holds for 7, but not for 15. Okay? And the point being that 7 is prime. So modulo primes, these equations have either 0 solutions, or 0 solution, or 2 solutions. Okay, so that's number 1. And you give it a name, you call the set of numbers which are squares quadratic residues. So 2 is a quadratic residue and 6 is not a quadratic residue. Okay, so clearly, because every number either has 2 square roots or none, the set of quadratic residues, right? So the function that maps x to x squared is a 2 to 1 function. Therefore, the set of quadratic residues is half the range, which is p minus 1. Right? So half residues, half non-residues. Good. Okay. So what does this all have to do with anything? Okay, fine. So find this notion of Legendre symbol, which is 1. This notation says the Legendre symbol of A, which is 1 if A is a square, minus 1 if A is not a square. A is no notation. All right. So now we come to the computer science question. Math. Question 1: can you check? Given a number A, can you check that it is a quadratic residue? The x squared equals A has, the fact that x squared equals A has a solution is checkable in polynomial. Question number 1. And if it is, a square, can you find the square roots? There's one, there are two. And they are negatives of each other, right? So can you find this in polynomials? Okay. So this is a computer science question. And the answer turns out to be yes, if P is prime. Okay, very, very important. We'll later see what happens if P is not a prime, and then these questions become hard. Right? So how do you, I mean, what is the criterion to check if a number is a quadratic residue or not? Okay, here's the criteria. Write the number a as g to the power x, okay, where x is a unique number between 1 and p minus 1, inclusive. Check if that x is even. If it is even, it's a quadratic residue. The number a is a quadratic residue. If it's not even, it's not a quadratic residue. This is the characterization. Yes? Good? Okay. Proof? You guys figure it out. It's easy. Okay. So in one direction, if x is even, right, so it's g to the 2y, yeah, for some y. G to the y is a square root. The other direction, do the same thing. Okay. All right, so does this theorem give you a way to check whether a number is a square or not in polynomial time? It's a nice theorem, for one. Yes, no?
I think not, because you can't take the discrete log.
I mean, yeah, so I mean, this theorem says, A, compute the discrete log x, and then check if it's even or odd. But thank you very much. You didn't do very much because I can't compute discrete logs. Okay, so it's a nice characterization, but it doesn't give me a polynomial time test. Yes? All right, so here is a polynomial time test. Here is the effective characterization. It says that a number a is a quadratic residue if and only if that condition is true. If and only if a to the p minus 1 over 2. A is a quadratic residue if and only if a to the p minus 1 over 2 is 1 not b. Now, assuming the truth of this theorem, which I'll show in a minute, is this, does this give you an effective characterization? It does, because all I need to do is take this number a and raise it to the power p minus 1. And we know how to do exponentiations, even with a very, very large number in polynomial time. How do you do it? Repeated squaring. Right? This is something you saw in 6046 or even before. So this does give you, theorem 2 does give you an effective characterization. Okay. But theorem 1 is good to keep in mind because it will help us think about these processes. So it's good to keep both in mind. So why is this true? I don't know. So in one direction, suppose A is a quadratic residue, right? So A is equal to b squared mod b. Yes. So what is A to the p minus 1 over 2? This is b squared to the p minus 1 over 2, which is b to the p minus 1. And what is b to the p minus 1 mod b? It's 1. So that's what Lagrange theorem says. You take any number to the power of the order of the group, you get it. Lagrange, Fermat, you know, all these things are the same thing. Okay? So, how about the other way around? Suppose a to the p minus 1 over 2 is 1 mod b. A, you can write A as a number in ZP star. So if you have a generator of ZP star, you can always write it as a g to the I. Mod b for some I. Right, so a to the p minus 1 over 2 is g to the I times p minus 1 over 2. And we know that this is 1. Right? So what does this mean? This means that I times p minus 1 over 2 is a multiple of p minus 1. And that could only happen, right? So this It can only be true when I times p minus 1 over 2 is a multiple of p minus 1, which can only be true if I is even. Okay. If I is even, we know that g to the I is equal to first. Yes. So this is all. Questions? Any questions? Totally elementary. Yes.
This is slightly unrelated, but when we say we want to find something in polynomial time, do we mean in the number of bits in p?
Correct. Correct. It's always, so polynomial is always in the input length, right? So you think about the input, it's g to the x. It's a number from 1 to p, which is log p bits. So polynomial time always means polylog p in this context. Yes, indeed. Good. Yeah. So you can check whether a number is square or not. Also turns out that if you can compute the square roots of a number. If a number is square, you can compute both its square roots. And here is a way to do it when p is 3 mod 4. P is 1 mod 4, but in the general case, there are several other ways to do it. I'm not going to describe it, but you should look at the lecture notes, the number theory lecture notes that we posted on the. Okay, so all these things can be done. Yeah, so that's it. So the punchline of all these theorems is that given g to the x mod p, you don't know what x is, but you can compute the least significant bit of x in polynomial time. Yes, why? Because given g to the x, I can compute whether it is a square or not. If it's a square, the least significant bit of x is 0. If it's a non-square, it's 1. There you go. Right? So I can compute this. So it is a horrible protocol. It gives you the sense of security, but it isn't. So who can cheat who here? Again, Bob can cheat Alice. Right? Bob can look at g to the x and he says, well, I know what b is. Compute this, whether it's a square or not. Yes? Not very good. Not very good at all. All right, so then the question is, are we really doomed here, right? I mean, is this ever going to work? Is there some other bit, okay, that, say again? The second least significant bit, again, doesn't work, but you have to see, you have to be a bit more, you have to do a bit more work. Depends on what p is. So if p is, p minus 1 has, is even, for example, you can still attack. Okay, so least significant bit doesn't work. The second least significant bit I claim that doesn't work. So what could possibly work? Yes?
Parity?
Parity of all the bits of, yes or no?
Parity of the number of ones.
What do you mean by that? The parity of the number of ones. Yeah, which is parity of the bits, right? Well, you know what? That's a homework question for you. Okay, it's a good, could work, may not work. I've never tried to prove it or break it. I don't know. Unless Alex, can you break it? And Josh, can you break it? Sorry. No? Okay, therefore it's a homework question. It's a good suggestion. Okay, if LSB doesn't work, I go all the way to the other extreme. I say the most significant bit. Okay. That's my, yeah, so some bits different. Okay, so that's what I'm gonna show, that in fact the most significant bit is very hard to predict. The most significant bit of x is very hard to predict, meaning what? You can predict 50%, right? You toss around a coin, it's 50% probability. But anything better than 50% you cannot do. That's what I want. Okay, but we'll get there. So before we get there, let's define the notion of hardcode predicates. Okay, so what is a hardcode predicate? Hardcode predicate is associated to a one-way function. So remember, a one-way function is this. X, you can easily compute f(x), but it's hard to go back. A hardcode predicate is a function that acts, is a predicate. A predicate is simply a function that outputs one bit. That's that, right? It is a predicate that acts on x and outputs b of x, so b is the hardcode predicate. It is easy to compute given x, so b is a polynomial time computable function, right? But given f of x, given x it's easy to compute, given f of x it is very, very hard to compute. Okay, so it's hard to compute given only. And not only that, that's not good enough for me. What I want is that it's hard to even predict significantly better than random guess. So it's a bit, it's a single bit, right? I can always predict it with probability of half. But I want to say no algorithm can get it right with probability half plus 1 over polynomial in n for any polynomial. Another way to say it is that for every adversary, yes, this is the definition, for every predictor P, for every adversary P, polynomial time adversary, there is a negligible function such that, you know, the guy, probability that the guy given fx predicts bfx is half plus negligible, at most half plus negligible. The advantage over half that he gets is tiny, it's negligible. It's this way. Okay? Okay, so now, if you, instead of the sum bit, you put in a hardcore predicate, hardcore bit, in the place of some bit in that protocol, you would get security. Why? Because when Bob sees f of x, or rather g to the x in this context, he won't be able to, it's as if it's random. He doesn't know what it is. Therefore, the best he can pick c is just truly random. So that's because of hiding. That's because of this property. And Alice cannot change her mind, so she just, no matter what she does, even if she's not polynomial time, she just cannot change her mind. And therefore, Bob cannot be cheated. Right, so this is the right notion. This would actually give you security, fairness in that way. Okay? So now the question is, do hardcore predicates exist? Right? I mean, it's nice to define things, but if they don't exist, not very good. Right? So it turns out that, you know, if you look at specific one-way functions, let's say the discrete log one-way function, RSA, we haven't defined it, but we will. Each of these functions have very natural hardcore predicates. So discrete log has the most significant bit, appropriately defined, is a hardcore predicate. RSA, it turns out that the least significant bit is hardcore. I think for RSA, actually, every bit is hardcore. So on and so forth. Okay? And then you could ask, look, is this really what you want to do? For every new one-way function that someone comes up with, do you have to like stare at it and try to see which bit is, you know, sometimes it's the most significant, sometimes it's the least significant, sometimes it's the other bit, sometimes it's the parity, maybe not, who knows, right? And you have to prove these things, as we will do for the most significant bit. The question is, do you have to prove these things starting from scratch every time someone comes up with one? It turns out that you don't have to. This is really beautiful theorem of Goldreich and Levin. One second. And they came up with a hardcore predicate, one predicate to rule them all, right? So this is sort of one predicate, or really class of predicates, that works for any one-way function. So you don't have to design a new predicate for every one-way function. You don't have to do an analysis anew. This we won't see today for the next class, but we will see the first of these things. Yes, sorry.
What about MD5 or has a hash function, like a get hash function and there's the least significant bit of the function?
That's how shall I put it? It's an interesting question. I don't think anyone has really sort of analyzed this sort of thing, because as you will see, a proof that something is hardcore, someone has to prove, right? I mean, you can't. I mean, I can't claim that the least significant bit for discrete log is hardcore. Well, I can claim it, but I would be wrong. Right? You need to prove these things, right? And we don't know a proof that any single bit of MD5, for example, is hardcore. It's a very interesting question, and it's a very interesting question. We should try it. Okay. So that leads us to the question of what does it take to prove? I can't claim these things. We're not in 6857, we're in 6875. Okay? We have to prove these things. How to prove that something? And as usual, we prove these things by reduction. Right? So we say, if the statement that you want to prove is if discrete log is one way, then the most significant bit is hardcore. The way we prove these things is by contradiction. Okay, to take the contrapositive. So assume that the most significant bit is not hardcore. Yeah. So in other words, suppose that there is a hypothetical predictor that gives f of z. In our case, it's g to the z. Predicts b of z. In our case, the most significant bit of z. with significant advantage, half plus 1 over polynomial n. Suppose that it exists. We are trying to prove that it doesn't, right? Then I can use this guy to design an inversion algorithm that takes g to the x and produces x. In other words, take the opposite of what I said. If this function is one way, if f is one way, then there is no such predictor. Because if there existed one, I would have used it to invert. Okay, so this is the way. This is the canonical way crypto proofs go. Counterpositive. Reduction, prove the counterpositive. Right? So this is what we want to show. Now, the statement of the type that you said, right, to prove it, you need to show such a reduction. Assume that there is an algorithm that takes MD5 of x and predicts the least significant bit of x. You have to somehow use this algorithm to invert the MD5 function. We don't know how to do it. Because MD5 doesn't have nice structure. It's a very complicated function. That's answer number 1 for you. Answer number 2 is that if instead of the least significant bit, you pick a random parity of a subset, random subset of the bits, then you can prove the statement for MD5. In fact, you can prove the statement for every one function. I don't care what that one function is. Right? That's the Goldbeck-Leibniz theorem. Yes? Does that make sense? So specific bits, it's very hard to prove security, but a random bit, a random parity of bits, it's always easy to prove. Okay, but that's something that we'll do in the next class, so let's leave that aside, this random parity equal to 11 bit. We'll try to do it for more significant bits. Oh, yeah. So I gave away punchline of the slide. Doesn't matter. Okay, so here's the question. How do I define the most significant bit of x? There's an obvious way to do it. Write down bits 1, 0, 0, 0, 0, 1, 1, 1. Take the first bit. Yeah, that's a significant bit. Except that is not a hard-fork predicate for discrete log. You see why?
Because p may not be a power of 2.
Yeah, p minus 1 over 2. If it were a power of 2, then it would be an unbiased bit. But if it's not, right, that bit itself is biased. It's more likely to be 0 than 1. Yeah? So that's no good. I mean, the adversary can predict the bit without being given anything, which is not good at all. So the first thing to do is to define an unbiased bit. And this is morally the most significant bit. It's not actually the most significant. Okay, so what is the most significant bit function? It's 0 if x is in the first half of p minus 1, 1 to p minus 1, or 0 to p minus 1, or 0 to p minus 2 is what I'm thinking about, right? So it's between 0 and never mind. It's between 1 and p minus 1 over 2 inclusive. Then it's 0. Outside, it is 1. Okay, so this cuts the domain in half, and this makes it unbiased. Yeah? Does that make sense why I'm saying this? Because, it'd be pretty stupid to design a predicate that was biased. In particular, that would give Bob an advantage without seeing anything to bias this, bias the part. Okay, so this here. Make sense? This is most significant bit for us. It's not the most significant bit. It's the bit that decides whether x falls, the discrete log falls in the first half or the second half. It's clear why we are doing this? With me? Thought up? All right, so now comes the reduction. Okay, let's do it. Reductions are algorithms, right? You have to come up with, well, what do you have to come up with? You have to come up with the discrete logarithm algorithm. An algorithm that solves the discrete logarithm. Of course, I can't do it. But I have this magical oracle that predicts the most significant. It's a weird type of algorithm, like Shafi said, in the very beginning, right? It has access to, it is algorithms that have access to oracles that do strange things. You want to use these strange things to do even stranger things. Those are reductions. Okay, so this is what I want to, suppose you have a predictor, right, that given g to the x outputs the most significant bit of x, most significant bit in the way we defined in the last slide, for start saying, right? Let's assume that this guy is a perfect predictor to begin with. What does it mean, a perfect predictor? It gives you the right answer for all p, g, and x. Can we use this to find the discrete log? That's the question. So, given predictor, so for Fred, this is a perfect MSP predictor. Design a discrete log algorithm. Log. That's our goal. That's what we're trying to do. Okay, let's try. Let's give it a shot. Now, look, what is this predictor going to give? Every query that I make, every sort of time I invoke the predictor, right, on g to the x, it gives me 1 bit. 1 bit. That's not very much, right? I cannot hope to invoke this predictor once and try to get something out of it. 1 bit, I could have guessed it myself, right? I have to invoke this predictor many, many times in a nice way and extract enough information from him to piece together the discrete log. Okay, let's try. So here is my discrete log algorithm. I like boxes. I'm drawing them. Which gets what? G to the x, right? And it wants to find x. That's it. It has access to this predictor, which is a perfect predictor. Sorry, it gets P, G, and G to the x. Okay, so what does this box mean? I have an algorithm. I have this little box that does the prediction. Right, always computes the most significant. I have to use this as a subroutine to find this tree. So, you know what? Let's start by doing one thing at a time. Can I use this box to find the least significant bit of x? Yes, no?
I think we can calculate like b by b.
Good, good. Let's get there in a second. But just the least significant bit. Tell me yes or no. Yes. Okay. Good.
Can you do that without the box?
Precisely. Precisely. Why do I even need the box? I mean, I showed how to compute. Yeah. See if g to the x is a square or not. I can do it by myself. No box. And I. So, number 1, compute least significant bit of x by myself. I am the box. I am the discrete log box. Yes, that's myself. All right. So let's let x be. Let's write x as in the bit representation, right? So that xk minus 1 up to x0. These are the bits, and k is log p, roughly speaking. Right? So I just computed x0. Yes? Just computed x0. Now what do I do?
Use the box to compute the most significant bit.
Say again?
Use the box to compute the MSP.
Say again?
Use the box to compute the MSP.
Use the box to compute the MSB. Good, we will get there in a second. But here is another idea. Okay, so tell me why it's wrong. So if I know what x0 is, I can sort of take it off, essentially. Right? So compute g1, sorry, this is y, call this y, give it a name. Set y1 to be y times g to the minus x0. Yes? So that would erase the least significant bit. So make it, so that would make it xk minus 1 up to 0, right? And now compute the square root. So I didn't show you how to do, but I claimed that you can compute square roots in polynomials, right? Set y1 prime to be the square root of y1 on t. So then what happens? This is the, taking square roots halves the discrete logarithm, yes? So you would make it, you would shift this whole sort of bit sequence one step to the right. So you make it 0, xk minus 1, up to x1. Yeah? So now I know g to the power this number. Yes? Do it again. Okay. So compute x1, which is really testing whether this number is square or not. Zero it out. Take the square root, shift everything to the right. Keep doing it. And you're done.
Yeah, I'm just curious, is this how you compute the second least significant bit?
This doesn't work, number one. So, I mean, I could try, but sometimes it works. So you have to be careful. Okay, so why doesn't this work? Ooh, 3 hands. Okay, coin toss, let's say.
When it was square root, there is a plus minus uncertainty with
Beautiful, right? So when you compute square root, I say, which square root? I mean, the square root algorithm is going to give you 2. One of them, if you look at the discrete log, if you look at the exponent, it's going to look like this. And what is the other one going to look like? Any clue?
P minus.
It's P minus that. No, it's a little different. So the number itself, you're right, is P minus that. Absolutely, right? There are 2 square roots. The number, negative number, that is P minus that number. But if you look at the exponent, what happens, right? So, again, you're absolutely right. Right? So square root y is plus minus z. Yeah? So z of P minus z. One of the square roots, if you look at the exponent, it'll look precisely like this. It'll look like this number divided by 2. What is the other number going to look like? It's negative 1 times, right? So discrete log of, let's say, z. I don't know which one, actually. Let's just say z is g to the power 0, xk minus 1, up to x1. Right? And what is discrete log of minus z? Sorry. It's this number. What is discrete log of minus z? It's the discrete log of minus 1 plus the discrete log of z. What is the discrete log of minus 1? It's p minus 1 over 2. Keep doing g to the p minus 1 is 1, g to the p minus 1 over 2 is minus 1. So this is p minus 1 over 2 plus 0 xk minus 1. Yes? So far so good? But I don't know which one is the case. It could be that the square root algorithm gives me 2 numbers. One of them is going to look like this, and the other one is going to look like this. And I don't know which one. If I, by mistake, pick this one instead, and continue with the algorithm, I don't know what happens. This number is write down p minus 1 over 2 in the bit representation and add them together. Who knows, that might corrupt x1, depending on what p minus 1 over 2 is. Right? Yes.
Could you figure it out using the most significant bit?
Yes, that's what I want. So really what I want to do is I'm getting 2 numbers here. One of them, if you take the discrete log, right, it's a number that starts with 0, so it's less than p minus 1 over 2. The other number, by design, is bigger than p minus 1 over 2. So I want to just figure out which of the 2 is the case. if I know which of the two, I'll continue. Yes. And that's the idea. That's where I use the most significant bit predictor. So far, I didn't need them at all. Yes. So here is the algorithm. So compute these guys sort of bit by bit. At any point, when I get the square root, test what its most significant bit is. If the most significant bit is 1, I say take minus c, go to the other one. If it is 0, I say, well, this guy is good. Its discrete logarithm is a small number, 0, something, something, something. This is the only place I use the predictor. With this guy, I would actually zoom in on this number. Right? Then I can continue. Then I can keep extracting bits one at a time. Yeah, does this make sense? Good. And the beauty of this is that, well, several things. One thing is that it actually uses the fact that the least significant bit is easy to compute to show that the most significant bit is hard to compute. Nice, yes? The other thing is this idea of, well, okay, so we have a gun there. Random self-reduction. What random self-reduction? There's no random here, right? This whole thing is deterministic, yes? Yeah, I compute square roots. But to the extent that square roots, you can do it without randomness, compute square roots, ask the predictor, do something, and then keep going. Yes? No randomness. Yeah? What random self-reducibility? Yes?
So when you do these reductions, we're assuming that like our output is perfect, right?
Output of what? Output of the predictor.
Yeah, the predictor.
Here, yes. But that doesn't prove my theorem, right?
Yeah.
My theorem should be able to work with predictors that succeed with half plus.
Yeah.
Yes? So this doesn't prove the theorem. It is, as the title says, it's a proof for a simpler case. Precisely. Right? So I have to work with predictors that lie and cheat all the time, like, except for 51%. The probability that it gives me the right answer is 50.00000. How do I? So this actually is the case, for all the things that we'll see in class. The first thing is try the simpler case. Try working with the simpler. If you cannot do it, then by definition, in some sense, do the harder case. Then a lot of hard work goes into kind of working with imperfect predictors. Let's try. I'm not going to be able to finish the proof, but we'll post lecture notes and slides. So what I want to do in the next 12 minutes is to give you an idea of how to handle imperfect predictors. These predictor algorithms won't be perfect, imperfect in the sense that they'll succeed with probability that they'll output the right bit, the right most significant bit, is this. Guaranteed to be at least this. That's all we know. Okay? How do you do it? Well, first thing to check for yourself is that if you try to run this reduction as is, with this imperfect predictor, you're going to be in trouble. Half the time you get the wrong answer and you will, the first time you get the wrong answer, you're already in trouble. So that doesn't. All right, so here's what we're going to do. Okay, hey, here's an answer. turn it into a perfect predictor. Okay, that's an answer to this question. That doesn't help with me. But that's what we're going to do. We're going to work with this guy, feed him like many inputs, left, right, and center, and somehow we're going to force him to give us what we want. Okay. So let me do it one step at a time. Let me define two numbers. Define two numbers. This doesn't use anything, I'm just defining things. P0 is a probability, that's the predictor, on input P, G, and G to the X. Output 1, conditioned on MSB of X. 0. P1 is the probability with the predictor on input P, G, X. Output 1, conditioned on MSB of X. Okay, so these are two numbers. Just analyzing what is going on with this predictor. So what is this number? You know, I pick a random x whose most significant bit is 0, number from 1 to p minus 1 over 2. What is the chance that he gives me 1? 1 is actually the wrong answer. Yes? This is, again, pick a random number with most significant 1. What is the probability that he gives me 1, which happens to be the right answer? Yeah? So the intuition is that P1 minus P0, these numbers have to be different. Yes? Because if he says 1 with the same probability given most significant bit 0, as he says 1 on input most significant bit 1, he's not doing very much. He's guessing at random. Okay. But we know that he's not guessing at random. He's getting some advantage. So it must be that these numbers differ by significant amount, significant being 1 over P of n. Yeah, so this is something you can compute. Why? Well, what is the probability that the predictor is, you know what, I'm going to, just try and leave this for you. So plain P1 minus P0 is at least 1 over P of n. In fact, I would even say it's 2 over P of n. Doesn't matter, some 1 over 4. Yes? This is something you can compute using the fact that the adversary succeeds with half plus 1 over P of n. You do the right thing, conditional probabilities. Okay, you can see that. Okay, that's the first step. But, you know, that doesn't help me very much, yes? Because P0 and P1, they're different, but what are P0 and P1? I need to know these guys to work with this adversary, yes? The good thing is that I can estimate these quantities. Okay? So I can come up with estimates of P0 and estimates of P1, which are arbitrarily close, arbitrary 1 over polynomial close to the real values, such that P0 minus the estimate of P0 is at most epsilon. And therefore, and also, not therefore, but also 1 is epsilon for any choice of epsilon I want. Okay, how do I do it? I run the adversary many, many, many times. Keep picking g to the axis of my own choice with most significant bit 0. Keep feeding the guy his values. Take the average of his outputs. Take the essentially the number of the fraction of times he comes up with 1 in both cases. And that by law of large numbers, or Chernoff, if you will, gives me a pretty good answer, as good as I want. So this is something that, okay. So if you write down this line where P0 is here, P1 is here, I know that they differ by at least 2 over P of n. I can get numbers that are very close. Let's look at P1, which are very, very close. Epsilon, epsilon. Okay. So this thing. So not only do P0 and P1 exist and they're different, I actually have a handle on them. That's the second step. This is a mental step, mental experiment. This is the actual step where I run the predictor. Here's what I do with these things. Now, predictor prime, which is the better predictor, does the following. It first runs this step, compute, estimate P0 and P1. And now it says the following. It says, well, let me compute, let me do random subtractions. So this is the first step where random subtractions come in. Predictor prime gives us input y. Runs predictor, the old imperfect predictor, on y times g to the r for Ri for many random Ri in the range 0 to t minus 1 over 2. Yeah, so what am I trying to do? I have y, I'm trying to compute the prediction of most significant bits on the discrete log of y. That's what I'm trying to do. Very well. I'm going to try to do it really very well. The way I do it is I randomize this guy y many times by multiplying the g to the ri. Where does ri come from? It's a random number from 0 to half the range. Right? The point being that if I add a small number to the discrete log, right? So this guy is g to the power x plus ri. There's a good chance that this ri doesn't flip the most significant bit. That's what I want. That's my goal. That's what I want. Yeah, that's what I want. But do I get what I want? It's not clear, right? Let's say x is actually close to p minus 1 over 4. Okay, it could be anywhere I want. If I add a random number from this range, half the time the most significant bit stays the same, half the time it flips. Yeah, so this is not completely clear what I'm doing is sufficient. But one thing I can say is that if x lives in the range 0 to epsilon p, epsilon, think of it as a very, very small number, 1 over a very, very small polynomial, 1 over a very, very large polynomial, right? Or it lives in p plus 1 over 2, p plus 1 over 2 plus epsilon p, right? It lives very close to 0 or p plus 1 over 2. Then when I multiply this with g to the ri, or in other words, I add ri to x, it doesn't flip over. What is the chance that it flips over? It's essentially epsilon. Right? So assume for a moment that x actually is special in the sense that x lives in one of these two ranges, then this process almost never flips over the most significant. Okay, so now what I'm going to do is take the average. The average of what the predictor says on input yg to the ri, right? And if it is close, so let's say this is called this estimate of y. If estimate of y is close to estimate of p0, say 0, else say 1. Okay, so that's what I want. Yeah, so for these special x's, I'm essentially randomizing the discrete log to be the same as what the discrete log of y is, more or less. There are imperfections in all sorts of places. But yeah. And if I keep doing this, I know that the adversary gives me the right answer 51% of the time. So if I do it a million times and take the majority, I'll get the right answer with very, very good. Okay, so this is what I do. Yeah, I can prove that this works. I'll leave this to the lecture notes. And then I'm still not done. What? This only works for a special x. What do you mean a special x? What is the chance that x is special? It's epsilon, right? It only works for an epsilon fraction of the x. So what do? I say, well, here's the procedure. I designed it, I'll prove it. It only works for any special x. I want to use it to work for any x. What do? I take my y, the real number that I'm trying to compute the discrete log, multiply by g to the r. Okay? What is the probability that it's special? It's epsilon, 2 epsilon for that matter. Okay? Run the procedure with it. If it works, if it is special, it'll work, right? And I'll get the discrete log. If it's not special, no problem. Take the same y, multiply it with g to the random r, keep doing it. So if 1 over epsilon twice, it'll work.
How can you tell if it was right or not?
Good, beautiful. So you can, because you can compute the function in the forward direction. When you run this whole process, then you will get a predictor prime, yes? You will plug this predictor prime into this algorithm. Instead of predictor, you will put predictor prime here. Run this whole massive process. Out comes, the output of this thing is a candidate for a discrete logarithm. That you can check. And you know that if this number is special, the number y that you fed into this predictor prime is special, you will get a good prediction and you will get the discrete logarithm.
Wait,
Yes.
so if this succeeds with like probability at what? epsilon-ish time, then and then you do like n steps.
Yes.
Then you're not succeeding very often then to go back and check the discrete log.
Very good. Okay, catch me every time. The point is, I take my y, I compute y times g to the r. Right? Now I'm counting on the fact that this guy is special. Okay, let's say it is special, probability epsilon. Now I run this procedure. What does that mean? This procedure feeds, runs predictor prime. I'm not going to run predictor prime with many different z's. Right? It has to be that all of these z's are special for my algorithm to succeed. But you know what? All these z's are special. If I start with a special number, what is a special number? It's a number that lives in a very small range. What am I doing in each of these steps? I'm basically halving the number. So if a number is special, half of it is special too. So all the inputs, all the things that I feed into this predictor prime will be special, and I'll get the answer with probability. So let's fix a special number. This whole thing will work with probability very close to 1. And then I keep doing it until I hit a special number. I know that if I hit the moment I hit a special number, I'll get the discrete logarithm. That's it. There's a lot here. There's a lot going on here. Really, the one really important thing to understand here is this algorithm. How do you prove these things for a simple case when you have a perfect predictor? Then you have to do a lot. We'll post the notes. For those of you who are a bit more advanced, should go and read.